All right. So I'm Marius. I'm going to talk about how to use IREE on bare metal platforms. So first of all, I give you a short introduction on what IREE and more specifically what TinyIREE is. I will walk you a little bit through how you can run it on bare metal platforms. So we have an example repository, but I also walk you a little bit to what do you need to do with regards to CMake, what should the toolchain file look like, what do you need to take into account regarding the linker script. And then I'll tell you something a little bit about some options we have within IREE and which are of special importance for TinyIREE, like IMC and the inline haul, and what is the effect on the program size as well as the execution time. And I will finish my talk with a short example use case, which we actually did at our research institute and what we use TinyIREE for. So for those of you who attended yesterday, Stella already got an introduction. I gave an introduction to IREE. So IREE is essentially an MLIR-based machine learning end-to-end compiler. And TinyIREE is a subset of IREE options, which we use to generate a compact workload. So for the host code generations, this means that we are mainly interested in the LLVM backend to generate CPU code and more or less also in IMC. I will come to that a few slides later. And for the device code generation, we mainly care about LLVM. So SPIR-V or VMVX, that's not really of interest for us when running IREE on a bare metal ARM device. So TinyIREE was essentially first presented in an article which appeared in IEEE Micro. This was driven by Cindy Liu from Google. I was co-authoring this author, but also other authors from the IREE team participated in this effort. It's available open access, so if you want to take a look into it, it's not behind a paywall. You can just download it and go for it. And TinyIREE's runtime library is essentially optimized for embedded systems, so for systems without an operating system, so-called bare metal systems. And we have IREE modules which can either be of VM bytecode. Also, you can use C source code, static libraries, and what IREE generally also provides you are shared libraries. But those are not of interest for systems without any operating system. And the IREE runtime itself, it includes a virtual machine and a hardware abstraction layer. But we actually only focus on the CPU, but the hardware abstraction layer somehow covers for you all the other device options where you technically can deploy your workloads to, like Vulkan, CUDA, ROCm, or Web GPU. So what do you need to care about when you want to use TinyIREE? So actually, we have an example repository which provides you all the examples. I'll guide you through, I'll walk you through on GitHub. So everything is open source. The samples can be executed on ST microsystems, STM32 MCUs, but we're also supporting Nordic ZOCs, or the ARM Core Stone 300 is also something you can run these examples on. So first of all, you of course need to get your compiler. And getting IREE is quite easy. You can just download the IREE dist tarball, unpack it, and you're fine. You're good to go. There are also alternatives. You can, of course, build IREE from source, but then it also involves building parts of LLVM, building MLIR. So you probably need a quite good performing build machine to do so. Otherwise, it's not fun. There are also options to pip install the IREE compiler, but you would need to build some additional tools from source. So the recommended way is essentially just use the IREE dist tarball, or if you want to have it in an even more convenient way, just use our bash shell script, which does this for you and will pack it the way you need it. So IREE is essentially, you can build IREE with Bazel, but if you want to build our examples, you will go the CMake way, and also IREE's primarily build system is CMake today. So when we build for an ARM bare metal device, you don't need to run build a compiler at all. So that's what we just grabbed with our IREE dist tarball. So you can just set, please don't build a compiler. We only want to build a runtime, which is then cross-compiled later on for your bare metal device. Furthermore, on the systems we are interested in, You don't need multi-threading support, so just turn the enable threading, set this flag to off. And you also don't need to build tests, and you don't need to build samples. Technically, you can build samples, but this flag is used for the samples which are provided within the IREE repository. So our samples don't care for this flag. You can build them just without setting this flag to off. And there are some more options which are quite important to build IREE. So first of all, there are different HAL abstraction layer drivers. IREE provides quite a few options there, but we are only interested for the bare metal system and the local synchronous one. So you can just set the defaults to off and just enable the HAL driver for the local synchronous HAL. It's similar for executable loaders as well as embedded ELF executable plugins. So you set your whole executable loader defaults to off and only enable the embedded ELF one. And you can technically also use the VMVX module. That's not necessarily the preferred way on a bare metal system, but we have examples in our repository to just showcase how you could do it. I will show you later on what is the effect on runtime and also on program size. So if you really have some workload which are interesting, probably you can also turn that option to off, but to build a complete examples, turn it to on. And for the executable plugin, we only need the embedded ELF one to go with the LLVM CPU backend mainly. If you ever have had experience in cross-compiling, you also need a toolchain file. If you do so with CMake, and there you set some very specific linker and compiler flags. So you go and set your specifications here, which is a no-this spec to essentially do not link anything into, and you provide what to link into by the next line. You only link in the math library and the C library. And that's mainly it. For the compiler flags, you need to specify your architecture. So actually the instruction set, you go here, we compile for an Cortex M4. So the architecture is an ARM v7EM. You set the float RB and also which FPU to use. This is specific, of course, to the dedicated MCU or CPU you are using. So this need to be carefully set. What IREE further requires you is to provide two function implementations. And that's the time now function as well as an IREE wait until function. So for the IREE time now function, we just implement this here as a dummy. It just returns zero. So we are not really able to do timings here, but we don't care for now. And for the wait until function, this is a little bit more complex one. We have implemented a dummy function within our repository. It's essentially returning a bool. So we are not able to wait here, but we don't care. And what's also important if you're targeting bare metal systems, you want to do some link times optimization. So the function sections which are not used as well as the data sections should be stripped. So you also put this into your compiler flags. And these ARM compiler flags and then needs then to be passed to the CXX or C flags. Furthermore, and that are IREE-specific options, you also need to set the LLVM target triple and the LLVM target float RB type. Because we are using for cross-compilation on ARM, we are using GCC, but for the device code, we use the LLVM backend. And therefore, you need to specify these two flags as well. My tip, just use and customize the toolchain file we provide in our repository. It's quite good documented and provides you options for different target platforms, so that makes it a lot easier. But just to let you know what are the most important flags here. Another thing, if you ever build a program for a bare metal device, is that you might need to take care of sections. So what you normally, if you're taking a look into Norman tutorials, the GOT as well as the GOT.plt sections are not linked into your executable. but you really need those to get IREE running on a bare metal device. So make sure you link them into your final executable. You can use the files we have patched for CMSIS and OpenCM3 within our repository, but you can also patch it by yourself. So essentially, this looks like you need to make sure in your assembler code or in your C startup code that those sections get copied, and you also need to define them within your linker script. So if you miss it, IREE will just fail, and you don't know why. So you can execute it, but you don't get the desired results. So that's why I would like to point out to this, make sure you have your GOT as well as GOT PLT sections included in your executable. So regarding program size and execution time, you can use the so-called MHC dialect. This is what we at Fraunhofer essentially worked on and put into IREE. As mentioned, IREE is a compiler as well as a runtime. So what on the compiler side, it generates you host code as well as device code. For the device code, at this moment, we don't care, but taking a look to the host code generation, what IREE does is it has a VM dialect, which is actually serialized into VM bytecode. And this VM bytecode is then compiled into your binary, and it's interpreted at runtime by the IREE runtime by a bytecode interpreter. And it actually calls into the hardware abstraction layer and the VM runtime. This is quite nice if you have to set up heterogeneous devices or have multiple device loads, but on a bare metal device, this is not the case. So what you can do is you can convert, or IREE does this for you if you set and use the right flags. IREE can convert the VM dialect to the MHC dialect, which is an MLIR core dialect that allows you to express or to generate C or C++ code. So we use this to generate C code, which is then finally compiled into your binary. And what it does is it does these does the calls into the VM runtime for you, and you don't need the VM bytecode at all. So that also means you don't need the bytecode interpreter. So that actually it reduces your flexibility, but that's fine for a bare metal device, but it also shrinks your executable size, which I will show you on the next slides. So another option is to go to take a look at the VM control. And normally the VM controls multiple threads, multiple devices. And there are some options which are more favorable for a bare metal single device. This is the so-called inline haul. So you don't have to set up your device because you only have one device. You don't need fences or pipelines. You just go and support your CPU-only target. And that allows you to this is called the inline haul, which is of a lower capabilities, but also of a smaller size compared to the complete haul, which IREE normally provides you. This is actually the execution model, which you can control with the flagged IREE execution model. So you can either go for inline dynamic or inline static for bare metal devices. We have different combinations supported. It also depends on if you're emitting VM bytecode to control your haul, or if you're using the C code generated by or with MHC. There are different combinations supported. Actually, it's quite convenient to just use our CMake modules, which do a lot of work for you. And there's still some ongoing efforts because, for example, the LLVM CPU backend only, at the moment at least, supports inline dynamic. But it would be nice to also have the inline static haul. I don't go into the details here, just want to mention it. To also support the inline static haul with the LLVM CPU backend, because that's the favorite backend actually for bare metal devices. And I now just showcase you the effect of this. So we have a simple matrix multiplication example, which just multiplicates two tensors with 1024 integer 32 elements. So the workload is really quite tiny. So the VM execution contributes significantly to your execution time, as well as to the program size. So when you build your program, and here I'm showing the data and the text section of our final Elf executable, using VMVX essentially results in the biggest or largest binary. And if you use the inline haul, you don't see much of improvement. But if you go for a static library, this shrinks down your executable size quite a lot. And using IMEC in addition to get rid of the bytecode interpreter even lowers or shrinks your executable more. And if you now use the inline haul, this has a similar effect. So using the static library plus inline haul, you get a smaller executable compared to just using the static library. But the most efficient is if you use static library plus IMEC plus inline haul, that gets you the smallest executable. And this is similar kind of for runtimes. So we measured it on an ARM Cortex M4, which is running at 46 megahertz. And we used it on an NRF 52840 development kit. And you can plug in a power profiler kit, which also comes with a logic analyzer. And what we did is we just toggled some GPIO opens to make sure we are aware of which code blocks are getting executed. So essentially what we measured is the overall run method within our executable. Then we separately measured the initialization of the initial buffer contents to get rid of those. We are not interested in. This is just overhead we are not interested in. We specifically measure the IREE VM invoke to have an idea how much does the invocation actually requires of our execution time. And we are stripping just some statistics printing as well as result checking. So we still are able to check if our results are correct, but we don't have included this in our execution time. And this finally gets you to the following results. So using VMVX, that's definitely not the fastest version. So it provides you with a big executable and it's slow. So it's not desirable to use it on a bare metal device. But what you can see here, using the inline haul, actually reduces your execution time. And it gets even better if you switch to the static library. And here we really see the effect of getting rid of the VM bytecode interpreter. So using IMEC really gets you a faster program. And combining this with the inline haul, combining or using static library with the inline haul has a similar effect. And here again, combining both options and using those with the static library gets you the fastest executable right now. So what we use it for, what we can think of, what could be interesting for TinyIREE is the following example use case. So what we do is, what we are interested in is doing sensor processing or processing of data provided by an accelerometer on device. So you can think of just really basic motions, like here showcased here, which are kind of dummy motions, but these are quite easy to reproduce in a experimental setup. And the idea is to process these information as close as possible to the sensor, so necessarily not even on the bare metal CPU, to reduce the energy consumption. And this can look like the following, though. That's what we actually already have realized. You can use an ISM 330 accelerometer sensor chip provided by ST, and this has also a so-called machine learning core on it. And the machine learning core is able to process decision trees quite close and directly to the accelerometer. And what we use it for is, it's kind of related to a wake-up detection. What we are doing even more pre-processing within this decision tree. And whenever the decision tree is not able to distinguish well enough between your motions, which is, for example, the case for the circular motions showing here, because it's not that easy to see if it's a clockwise circle or a counterclockwise circle and in which plane it takes place. Then the idea mainly is to run a full or a more advanced CNN, which is executed on the Cortex M4. And this is done by TinyIREE, essentially. That is what we TinyIREE use for. But there are more interesting sensors or platforms out in the field. So there's an ISM 330IS, and this is not limited on, to decision trees. So for the decision trees, you also need to use some proprietary tools to get this running onto your sensor. But there is a newer chip with an intelligent sensor processing unit, and this can be, and the workload there can be put onto it by compiling C++ code. So what we can think of is like how to incorporate this with IREE. So essentially we are going for a heterogeneous device. We can still think of like just using IREE to output C++ code, which is then compiled with the compiler you need, because I don't think this one is supported by any LLVM backend, so you need their proprietary compiler still. So C++ is the way to go. But you can also think about the partitioning problem, and that this can be maybe solved with an IREE. So not doing 2 IREE calls, which one generates you the executable or the workload for the ISPU and one for the CNN. It might also be possible to use IREE and let IREE essentially do all the work for you. And this really, you can really profit from this approach because it you can send your CPU longer to sleep when you design algorithms like that, and that can save you a lot of energy. So finally, I've just put some on my last slide. I provide some resources for you. So first of all, the IREE dev guide is of course a valuable resource to check the bare metal options. Our repository can help us as well. If you see that documentation is lacking, or if you have any issues, feel free to open issues, reach out to us. I further have to mention that it's not only possible to run IREE on a bare metal ARM platform. There's also the Springbok repository, which provides you with examples how to run bare metal ARM or how to run IREE on a bare metal RISC-V processor. Furthermore, the link to the article I mentioned where TinyIREE was first introduced. And if you're more interested in our use case and what we use it for, we have recently published an article in IEEE Micro which describes the use case a little bit more. Is available as open early access, and it's also open access, so it's also not behind a paywall. If you're interested, feel free to take a look, and I think now I'm happy to take your questions.
Any questions? Any questions from anyone on the bridge either? No.
Yeah, I can project my voice. Do you have a kind of a streaming model for this sensor? Are you streaming data through it, or maybe batch bulk processing or batch processing?
You mean for that specific sensor?
Yeah.
What we do is we put all the data we process into a FIFO, which is provided on chip. And if the decision tree predicts you some certain classes, we just wake up the